Welcome to this next video in our series. Today we'll start exploring Taylor approximation for multivariate functions. This will be a two-video introduction. So the first video, this one, will be about some notational conventions that will come in handy. And the next video will then formally introduce the Taylor approximation formula, which looks pretty similar to the one-dimensional case with the help of the notation that we're going to see today. So this starts a new section, 13.7, Taylor approximation of multivariate functions. So before we start with that, let's first recall what Taylor approximation looked like in the one-dimensional case. You will hopefully remember that formula. So for a function that maps from the reals to the reals, we introduced the Taylor polynomial and the Taylor series of f at x star. That is defined as the following series: sum from n to infinity, the nth derivative of the function f evaluated at x star divided by n factorial, and then times x minus x star to the n. And if you just take a finite part of that sum, then that is a polynomial. That's called a Taylor polynomial of the respective degree. And our objective now will be to generalize this approximation to multivariate functions. So we will generalize this formula to multivariate functions. Of course, the definitions of total differentiability can be generalized to higher order simply by recursive application of that definition. We'll only be interested in continuously differentiable functions anyway, so we just restrict our formal treatment to that specific case for the generalization. But let's just make a quick note about that. So the definition of total differentiability and also the results on that can be extended to higher order derivatives through recursion, and we will only formally define this for continuously differentiable functions. So we will restrict our treatment here to continuously differentiable functions. And in that case, one of the main results of total differentiability was that for continuously differentiable functions, the function is totally differentiable if and only if the partial derivatives exist and are continuous. So we can just use that as the definition for k times continuous differentiability. Let's do that. So first, a quick definition. As always, let x in R to the n be open. Let f be a mapping from x to R. Then the function f is called k times continuously differentiable if and only if all corresponding partial derivatives exist and are continuous. So then f is called k times continuously differentiable if and only if all partial derivatives of order k, so all derivatives of the form dk f dxi1 dxi2 and so on dxik, and of course some of these indices may actually be the same. If all of these exist and are continuous on x. And we'll introduce a quick notation for the set of all k times differentiable functions from x to R. That will be simply the set ck of x. Let me write that down. So the set of all k times continuously differentiable functions f(x) to R on x is denoted by the notation here is ck of x. And just as a very brief remark, you do know that you can add functions, subtract functions, and also multiply functions with some scalar. And it turns out these functions behave like vectors. So if you add two functions that are k times continuously differentiable, then of course the resulting function is also k times differentiable. And the same is true for scalar multiplication. So this ck of x is actually a vector space. Okay, now let's introduce some useful notation on these functions here. So that's the main part of this video, notation. We'll use a vector A. Oops, sorry. So let A be a vector that consists of components alpha 1, alpha 2, and so on to some alpha n. All of these are integers that may include 0. And then we define the following notation or notations. Okay, so first, an abbreviation for the sum of these numbers that will regularly be useful. So we just abbreviate that by absolute value of A. What we mean by that in this case is actually not the absolute value. Those are all non-negative anyway, so that doesn't make a lot of sense. What we mean by that is the sum of all these, alpha 1 plus alpha 2 plus alpha 3 and so on up to alpha n. Then we'll also define a handy notation for the factorial. We will write A factorial as an abbreviation for the product of the individual factorials. So that means alpha 1 factorial times alpha 2 factorial times and so on up to alpha n factorial. Then for some vector x, there's also n components. We will define what x to the a means. So for a vector x, that consists of x1, x2, and so on up to xn in r to the n, we simply set x to the a to mean x1 to the alpha 1 times x2 to the alpha 2 and so on up to xn to the alpha n. And last but not least, we also need differentials. So let's take a function. So for a function f in C absolute value of a x, so that means the function is differentiable absolute value of a times and we define a notation for the mixed partial derivatives here. We will denote by d to the a f of x the mixed partial derivative d to the absolute value of af over dx1 alpha 1 dx2 alpha 2 and so on up to dxn alpha n of x. So what we mean is differentiate with respect to x1 alpha 1 times, with respect to x2 alpha 2 times, with respect to xn alpha n times. Okay, so that's a neat abbreviation for writing these complicated terms with the partial derivatives. And we'll see those in action in Taylor's formula in just a few minutes. But before we do that, let's have a quick look at an example to get some acquaintance with this kind of notation here. Okay, so as an example, we are going to use a function defined on R2 to R, and we'll simply use the function f of x1, x2 is defined as 3x1, x2 plus x1 squared minus 2x2 squared. And we use some vector a. We have two variables, so that needs to have an alpha 1 and an alpha 2. And we just go through the possibilities up to some degree here to see what can happen with that. Okay, so first possibility, let's classify those by the absolute value of a. So the absolute value of a could start at 0, potentially the lowest possible sum of these alpha 1, alpha 2 is 0. That is the case if and only if a is the vector 0, 0, of course. Yeah, anything else will result in a higher value. What happens then is, well, a factorial is simply 0 factorial times 0 factorial, so that's 1 times 1, which equals 1. D to the a f of x, well, what is that? That's simply the 0th partial derivative with respect to 0 times x1 and 0 times x2. So that's just a complicated way of saying where we don't differentiate anything at all. So that is just f itself. Okay, and let's write this down once more. F itself is this term here. And finally, x to the a, well, again, that is x1 to the 0 times x2 to the 0. That's just a very complicated way of saying 1. Okay, so that case is more or less trivial. Next, let's have a look at the case where the absolute value of a is 1. Okay, what does that mean? Well, both entries are integers. So if the sum is 1, then one of the two integers has to be 0 and the other has to be 1. There's no other possibility. So let's just investigate those. We'll start with the case a is 1, 0. And in that case, the factorial of a is simply 1 factorial, 0 factorial, so that's still 1. X to the a is now x1 to the power of 1 times x2 to the power of 0, so that's x1. And dA f of x, well, that is df dx1 of x. So we differentiate f with respect to x1 one time. And just have a look back at the expression here. So what we get by differentiating that is 3x2 plus 2x1. Okay, so that is the case 1, 0. And now let's have a look at the other case. A could also be 0, 1. And of course, basically that just turns everything around. So a factorial is now 0 factorial, 1 factorial. Again, the result is 1. X to the a would be x1 to the 0, x2 to the 1. So that's 1. And dAf of x would now be df dx2 of x. So differentiating that expression here with respect to x2, we get 3x1 minus 4x2. Okay, so this is the cases where the sum of the entries is equal to 1. Let's investigate all the cases where the sum of the entries is equal to 2. So the absolute value of a is 2. And now, of course, there are 3 possible cases. Yeah? A could either be 2, 0, or it could be 0, 2, or we could have 1 and 1. So again, we just list all those and see what happens. So if a is 2, 0, then a factorial is 2 factorial times 0 factorial, so that's 2. X to the a is now x1 squared times x2 to the 0, so x1 squared. And dA f of x is d squared f dx1 squared of x. So we take this derivative here that we took with respect to x1 and differentiate once more. What we get is 2. So that's a 2. Okay. Let's also do 0, 2. That's more or less parallel to this case here. So a factorial is then 0 factorial 2 factorial. That's 2. X to the a is x1 to the 0 times x2 squared. That's x2 squared. And dAf of x is d squared f over dx2 squared of x. So we're taking that first derivative with respect to x2, that's this one here, and differentiate once more. Again with respect to x2, that yields a -4. Okay, and finally the missing case, the mixed case, a is 1, 1. Then of course a factorial is 1 factorial 1 factorial, so that's 1 this time. X to the a is x1 x2. And dAf of x is now d squared f dx1 dx2 of x. So this is the mixed derivative, and as everything here is continuous, it doesn't really matter whether we start with x1 or x2, so let's just take this one. That is the derivative with respect to x2, and we just differentiate that once more with respect to x1, and we get 3. So in this case that is 3. Okay, and as you can see, all the derivatives, whether mixed or pure, are now constants. So whatever we do in the next step, differentiating once more, will always yield a derivative of 0, no matter which case we start with. Okay, so we don't do the case 4 fully, we just take a quick note of that. All derivatives of order 3 are now 0. Okay, all derivatives of order 3 are 0. Okay, that concludes the example, and that concludes our introduction into the notation. In the next video, we'll use that notation to write down Taylor's formula for the multivariate case, and we're going to extend our example and see how the Taylor polynomials of that function look like. I'll see you then.